Let's see some problem scenarios involving uniform circular motion. You can take notes on page 6 for what you see here in this video. We'll look at forces and analyze how they apply to circular motion. Before we start, we need to make note of sign conventions. Forces that point into the circle toward the center are positive. Forces that point out from the circle, away from the center, are going to be made negative. Keep that in mind when you draw pictures with force arrows. The first scenario is where we have a ball connected to a string. It's being held above the ground and swung around in a horizontal circle. So the motion is all in this horizontal plane parallel to the ground. What forces pull on the ball? Well, there's gravity, of course, pulling it down toward the earth. Then we also have the string touching the ball. Anytime there's a string touching an object, there will be a tension force. And that tension force pulls the end of the string back toward the center. Remember that the string is slightly stretched because it's taut. It's slightly stretched. So that end, which is stretched out, wants to go back in to its relaxed length. When you analyze the forces, we can draw components of the angled tension. Theta is up here at the top of our right triangle. Tx and Ty now have labels, and if you look at this picture and you think about the fact that, hang on, the ball is not accelerating up or down, it's only accelerating toward the middle, that means that the vertical forces have to cancel out. Ty must be exactly as big as mg. They're just in opposite directions, so their magnitudes are equal. Since we've drawn components for tension, we can squiggle out of the hypotenuse. And when we look at the resulting picture, we can see what the net force is. Something is turning this ball, pushing it toward the center. Where does that centripetal, center-pointing force come from? It's Tx. That's the only one that doesn't cancel. So Tx is equal to F net. And if we take a closer look at the right triangle, we can write down tangent of theta. This is a trick, because tangent of theta is opposite, Tx is opposite theta, divided by adjacent. And if you isolate Tx, you cross multiply, get mg to the other side. Tx is equal to mg tan theta. But of course, Tx is F net. So that's the first scenario we can analyze. If you see a problem like this, you want to reproduce this kind of analysis from scratch. The next scenario is where we have one object orbiting the other. Maybe this is the Earth and this is a moon or a satellite. Perhaps this here is the sun and this is a planet. But we'll use the example where this is Earth and little m is a satellite. Okay, so the speed is perhaps this way, tangent to the circle. The velocity is always tangent to the circle in uniform circular motion. And the net force pulls this object toward the center. We know, of course, that gravity is the attractive force. That is the net force. Gravity is what pulls this thing and keeps it turning around in a circle in uniform circular motion. So if we plug in the equation for Newton's law of universal gravitation, we have g times the product of the masses over r squared. R here would be the distance from the center of the Earth to the center of the satellite. Now, the satellite is so small you can pretend it's just a single point. So instead, r would be the radius of Earth plus the altitude, or how high the satellite is off the surface. We can write this equation again, but in place of little r, put Earth radius plus the altitude of the satellite. The next scenario is a car moving around a circular track. And in this example, the car is traveling counterclockwise, kind of going around like this. So at the moment shown, the velocity is tangent to the circle. We know there's a net force pulling the car toward the center, but what is it pulling the car this way? Is there an invisible rope attached to the car? No, it's not that. It's not gravity. Gravity pulls the car down toward the track. You may recall, or you may deduce, it is static friction. The reason the car can turn is because of grip or traction, and that is another word for static friction. So the force of static friction provides the centripetal force, and if we look at the car from the side, from the front, so perhaps you're standing here looking head on as the car turns, what exactly are the forces that act? Gravity pulls the car into the track, pulls down. The normal force pushes up, and static friction pulls it toward the center of the circle. So the car is kind of moving around like this, where my mouse is going. The vertical forces have to cancel out because the net force is just toward the center of the circle. The car is only accelerating toward the center, not up or down. We know that these vertical forces cancel, and F net is static friction. We have an equation for maximum static friction force that we learned last year. It's the coefficient of friction times the normal force. The coefficient, remember, is usually a quantity from 0 to 1. It has no units, and it tells you how rough the surfaces are. But what if the car is moving around a banked path? So that means that literally this part of the road is banked, and over here it would be banked the other way. This is what you see if you go to a racetrack, and that banking helps the cars move faster. How does that work? Well, now gravity pulls down as always, but the normal force must be perpendicular to the surface. So there is a force still pulling toward the center of the center of the circular path. Where is that force coming from? Well, take normal force and break it into components. The y component has to cancel out the force of gravity because the car is not accelerating up or down, it's only accelerating toward the center of the track. So the car is not sliding down the bank, it's just moving around a banked road. In this case, the net force would be the x component of normal force. This is a simpler scenario, a simpler scenario where there is no friction. So the picture over on the left no longer applies. You would replace this with n sub x. The next scenario is a roller coaster ride. So here's the roller coaster at the top, and here it is again at the bottom. It may not look like circular motion, but if you imagine the full arc of this turn at the top, it makes a circle. And likewise at the bottom, this curved path, if you extend it out, makes a circle. Gravity pulls down on the car, and the force is always down. But over here, the normal force from the track also is acting. So the normal force is upwards, but is the force less, equal, or longer than gravity? The normal force has to be less, because to make this turn, there must be more force toward the center. The net force is toward the center of the circle. Over here, the net force has to be toward the center, and the center of the circle is now above the car, not below. So the normal force has to be longer in this case. And look at what that does. Remember what we said at the beginning. Forces pointing into the circle are positive, so mg is positive here, but n is positive over there. Forces pointing out of the circle are negative, so n is negative here, but mg points out, so mg is negative over there. It reverses the signs of the forces when you write out the net force. The final scenario is where you are standing on the ground holding a string with a ball, and you are flinging this thing around in a vertical circle. So it's moving toward the floor, then it's moving up toward the ceiling, and hopefully it doesn't hit the ceiling. And you could analyze the forces when the ball is at the bottom or when the ball is at the top. Of course, gravity pulls down in both cases, at the bottom and the top. What other object is acting? Well, the floor doesn't act because it's not touching the floor. The string is the only other thing touching the ball. So tension pulls the end of the string back toward the center. Likewise here, tension acts on the end of the string, pulling back to the middle of the rope. Now, when you look at the forces again, T is positive because it's in, mg is negative because it points out. So when you add up the forces to get F net, it's this. On the right side, though, both point in, so both are positive when we add them to find net force. What about at the side, you might wonder? Well, at the side, you have a force that is neither in nor out. What would this force do to the ball? Think back to the example of the person walking on the road and a car is coming. If you push with the velocity, the ball speeds up. And when the ball gets over to the left side, so yes, tension is pulling toward the center, tension is causing it to turn, but mg, while it turns, mg simultaneously causes it to speed up. As a result, the example you see here is not uniform circular motion, because at the sides, you have this other force, and the net force, if you added these together, the net would not be directly toward the center. Over here on the right, the ball would be speeding up as it falls down, and then over here on the left, it would be slowing down as it rose.